We want now to discuss the concept of conductors, or how the electric field or the current develops in conductors. They are saying that a conductor has an abundance of charge that are free to move. And we are going to consider two cases involving a conductor. The first case that we consider is that of an isolated conductor. And we say that consider an isolated conductor as shown in figure 5.2a. So we are considering this isolated conductor as depicted in figure 5.2a that is under the influence of applied field. The applied field is E. So you can see the field lines are directed as shown by the arrow. Now, when an external electric field E is applied, the positive free charges are pushed along the same direction as the applied field. So that is the first item that happens, that the positive free charges are pushed along the same direction as the applied fields. And as you can see, we have positive charges being pushed along the surface far away or from the source of the field E. So they are pushed away from one side of the conductor. And we also see that the negative charges move in the opposite direction. Also, as you can see, the negative charges accumulate on the surface of the other side of the conductor. We observe that this charge migration is very quickly, and this free movement of free charges achieves two things. One is that they accumulate on the surface, as we have observed, and form induced surface charge. And secondly, the induced charges set up an internal induced electric field EI. So what you observe is that these charges set up a new internal electric field strength EI that is equal and opposite that of external EE. Therefore, we say that EI is equals to negative EE. So what happens is that these two charges cancel out each other. And this leads to an important property. When they cancel each other, then we say that a perfect conductor having conductivity approaching infinity cannot contain an electrostatic field within it, simply because the one that was external is cancelled out by the one that is induced by the surface charges that accumulate on the surfaces of the conductor. And we say that a conductor, therefore, is called an equipotential body, implying that the potential is the same everywhere in the conductor. And this also agrees with the equation with the condition that we defined, that if a body is equipotential, then from one point to another, the potential is the same. Another way of looking at this is to consider Ohm's law that we define as J is equals to sigma E. And to maintain a finite current density J, a perfect conductor having sigma approaching infinity requires that the electric field inside the conductor also vanishes. That is, if this is approaching infinity, then E should approach 0, which is what we are saying here, that E approaches 0 as sigma approaches infinity. Therefore, if some charges are introduced in the interior of such a conductor, the same process happens. The charges will accumulate on the surfaces, the positive towards this side, and the negative towards that side. They distribute themselves very quickly in such a manner that the field inside the conductor will vanish again. Therefore, according to Gauss' law, if E, or the electric field strength, is 0, then the charge density rho V inside that material or inside this conductor must also be 0. Therefore, we conclude that the perfect conductor cannot contain an electrostatic field within it. So that is what we are saying, that E is 0, and therefore the charge according to Gauss' law must also be 0, because they are accumulating on the surface and cancelling out. And therefore we also come up with another statement that says that at the static conditions, the electric field strength is 0, the volume charge density rho V is 0, and therefore the potential VAB between any 2 points, if you wanted to consider your A to be there and B to be there, the potential between these 2 points will always be 0 inside the conductor. And this is the last thing that you are saying, that VAB is the potential difference between A and B in the conductor. And this implies that a conductor is an equipotential medium, since the electric potential is the same at every point. We now consider a conductor whose ends are maintained at a potential difference, as we have seen in figure 5.3, phase 1. So we have some potential difference applied across the conductor. Remember, the difference previously was that there was no conductor, it was isolated conductor, what we considered right here. And therefore, this is a different case in which we are considering that a conductor is maintained at a potential. So we note that in this case, electric field strength inside the conductor will not be 0, clearly because this positive is attracting the negatives, and therefore they are not accumulating here, but rather they are getting drawn towards the potential, towards the source. And the positives that are repelled by this potential at the source are getting pushed away from the conductor, and then they do not accumulate at the end, but they join the source as indicated. Therefore, the difference is, as I have explained, that there is no static equilibrium maintained in figure 5.3, since the conductor is not isolated, but is wired to a source of the electromotive force. This force compels the free charges to move and prevents the eventual establishment of the electrostatic equilibrium that was observed in section or in the figure 5.2, because we have seen they are not accumulating at the surfaces of the conductor, and they are getting drawn to the source. Thus, in the case of figure 3, an electric field must exist inside the conductor to sustain the flow of the current. And as the electrons move, they encounter some damping forces called resistance. So of course, as the electrons move from we are saying that electrons now will be moving of course against the field. We see it is the positive charges that give direction to the electric field, and therefore electrons move against the field. And as they are moving from point A to point B in the field, they are going to experience some resistance, the one that we are referring to as the damping. They are going to experience some damping forces that we characterize as resistance of the conductor. Now, based on equation 511 that we found earlier, we can derive the resistance of the conducting material as follows. Suppose the conductor has a uniform cross-section area S. So we can say that, of course, this is S, and it has length L. Of course, this is length L. The direction of electric field produced is the same as the direction of positive charges or current, I. That is true. That is what I've just said, that we normally characterize the direction of current or the direction of electric field as the direction of flow of positive charges. This direction is opposite to the direction of electrons, as I have mentioned, and the electric field applied is uniform. And therefore, the magnitude will simply be equals to V, the potential between those point A and point B, divided by the length L. That is how we have defined potential in the past. And therefore, we are just saying that the V applied divided by E gives us the value of E as defined in equation 513. Therefore, since the conductor has a uniform cross-section area, S, we may say that J, or the current density, is going to be given by I, current flowing, divided by S, the cross-section area. Now, from equation 511, which says that J is equal to sigma E, and 513 that we have just obtained above, we can see that we can replace J in this equation and by saying that this is equals to I over S. So we have replaced J on the left hand side of equation 514 with I over S. And we can also replace E on the right hand side of equation 514 with its value that we obtained at equation 513, and that gives us sigma V over L, as you can see in equation 515. And therefore, if you set V, or the ratio of V over I, as a constant R, then these other parameters can be represented by L over sigma S, and we can now say that the constant of proportionality associating V and I is definitely the one that we refer to as the resistance. And here we have just introduced one more parameter C, rho C, that we say is equals to 1 over sigma, which is, this is the term that we reverse to as the resistivity of the medium, whereas sigma is what we have already defined before as the conductivity of the medium. And from equation 516, we can say that it is very useful in determining the resistance of any conductor of uniform cross-section. And if the conductor does not have uniform cross-section, then we say that that equation is not applicable. However, the basic definition of resistance R is the ratio of V and the current flowing through the conductor I, and therefore that still applies. And therefore, equation 460 is actually, I have just restated it at that point. We say that potential between point A and B can always be expressed as negative integral of E from negative line integral of E from point A to point B. But you observe that we can therefore pick V to be represented by this in the numerator and I to be represented by equation 5.4 that is defined as the surface integral of current density J, and therefore when we replace these two we are able to define the resistance R. We only observe that in this equation we have changed or we have dropped the negative sign, since we know that the potential changes sign when the current changes sign, and for that reason we are observing that the current in our case is positive. And we are saying we are not going to utilize this one until the later chapter, which we will do later in the latter sections of this course. We now want to observe the idea of power. Power as produced in a conductor. Therefore, the conductor is flowing, having the conduction current. And we say that power is defined as the rate of change of energy in joules or the force times velocity. And of course, we can relate that by simply saying that since we can characterize the force that the electrons are experiencing with their velocity, by saying that the force that the electrons are experiencing in the conductor to be defined by that term, and they are moving with a velocity u. Rearranging this term simply gives us E and rho u, and we can identify rho Vu as the current density, because we know that current density is given by the amount of charge defined by rho V times volume per unit area flowing per second. And therefore, we can simply identify that this term is equivalent to J. And therefore, we end up with equation 518 that relates power with electric field strength and the current density J. And this is referred to as the Joule's law. And we can say that the power density omega P is the integrand of this term in equation 518. And we can simply say that divided by dV or dP gives you the power density WP. And this is equivalent to sigma E squared. And for a uniform cross-section conductor, we can always say that dV can be given by this formula. Of course, this is surface times length. And therefore, we can break up our equation 518 to have to take this form. we are breaking the dV, and therefore we are able to say that power is equals to voltage times current, or the potential times current, which can also be expressed as I squared R, which is the most common form of Joule's law as you use it in electric circuit theory.